And we start with a group, compact connected group. And then we literally take all possible loops, phase loops inside the group. And the conjugation action on G extends to a conjugation action on this omega G. And so you can talk about some kind of G equivariant theory on this spatial space of G. And the one that I'm going to talk about is in the literature called G equivariant Borel-Moore homology. But this is not the G equivariant Borel-Moore in the topological sense. So algebraic geometer use this notation, name. So I just keep using this name, but it's different from the.
Maybe we could just take a second, make sure that do we all understand what this means? Is omega G? Should we? Everybody okay with that? No, not everybody is okay with that. So we're starting with a group G, and omega G, we're looking at maps in the circle to the group, right? So
yes,
looking at loops on the group. Instead of looking at elements of the group, now we're looking at loops on the group that start and end at some point, which is the identity here, right?
Yes.
So we're looking at all loops that have to start and end at the identity element of the group. And now if we have two loops, we can compose them, right? We can take one loop followed by the other loop, right? Is that what you want to do, or do you want to just multiply the
pointwise multiplicity? So the G action on omega G. So I didn't talk about any extra structure on omega G itself. Instead of I'm only thinking about the conjugation action on omega G. So if I have
we're not thinking of omega G as a group. We're just thinking of omega G as being acted by conjugation. Exactly. So given any loop starting and ending at identity, if we conjugate the whole loop by an element, we get a new loop that also starts and ends at the identity. Does that make sense?
Yeah. Thanks.
Okay. So we just have to sometimes slow down a little bit because we'll use different notation and ways of talking about things.
Yeah, thank you. So gamma is a loop, and then G ends on gamma by conjugating. And then okay. So this guy I denote in this way. I put a little hat above. And it has two functorial properties. So one is that it is a covariant with respect to G equivariant maps, meaning that if I have X and Y, they act by G, and F commutes with the G action. And then you have the corresponding induced map on this homology. These are just abelian group or vector space. And then on the other hand, if you have a subgroup of G, then it behaves contravariantly.
So basically, we don't have to know, just to be clear, we don't have to all know in advance what this H hat G star is. We're just all being told that this exists, right?
Yes.
Satisfying these two properties.
Yes.
So for any space with a G action and any map X to Y, G equivariant means that the G action, the map is compatible with G action. We get that map, and then for any subgroup K of G, we get a restriction kind of map,
yes.
I guess. Okay.
Use the Borel rule of Borel cosection.
Borel cosection? What is?
There's a Borel construction given a space with a group action. You can form the Borel construction. I guess Yankee is asking if this is the Borel-Moore homology of the ordinary Borel-Moore homology of the Borel construction. No. It's not the same.
And then the one that you are saying would be what I would mean to a topologist, I guess. Maybe.
So one thing I know, like the different things that I've heard of, but one of the things is you can think of Borel-Moore homology as an ordinary reduced homology of the one-point compactification. Can you use that and the
No,
equivariance setting?
it's not
That neither of them you can use. Okay. To do something a bit more sophisticated then.
just something a bit weird. Yeah, actually, I talked to Dominic Joyce at some point about this, and then he told me that Newton the first has something called bivariant theory, which actually induced this cohomology theory.
But can we do it using like infinite sums of locally finite or whatever, infinite sums of chains that are
No, not really. That's a useful variable.
right, but with the I see. Yeah, okay, we can't do any of those things. Fine. Okay. So nobody here knows what that is actually, except you, then probably.
Yeah, but so I don't.
But that's okay, though.
That's okay.
If all we're expected to know is it has those two properties, then we're all okay.
So it is not defined for all topological. It's so you can first. It's quite easy to define for GCW.
Okay.
Okay, and then so okay, let me just talk about.
You don't have to go into detail about it if it's not a part of your plan, because it will take time. Only if we really need to know it. We can talk about it later.
Talk about it later. So using these two properties, you can give it an algebra structure. So one is I didn't say the first. So there's a Kuhn's type formula saying that these two guys together, you combine them, it becomes this one. Yeah, the same thing. And then when you pass to the diagonal subgroup, diagonal G, then this restriction gives you this map.
Yeah.
And then if you have a map from omega G cross omega G to omega G, which is given by, you just multiply the loops. So
okay.
if you have gamma 1, gamma 2, and then because G is a group, so you can multiply. So you can take gamma 1t dot gamma 2t.
Okay.
And that map is G equivariant with respect to the diagonal G action on the domain and the conjugation action on the target. Just because G gamma 1 T equal to G gamma 1. Okay. So you have two copies of this guy, and then go to one of these. So, and this gives you some map, and this actually forms an algebra.
So you're saying this behaves like homology with respect to spaces, you said?
Yeah.
And cohomology with respect to groups.
Yes.
Okay.
Yes, and this is the usual. So if you think of this as some.
I'm sorry. Now you're using the point.
Yes.
Now you're using the pointwise multiplication you were talking about before.
Yes, and this is this maybe you are more familiar with this. If I put the affine Grassmannian here, affine Grassmannian of the compressification of the group, and then instead of putting a G here, you put this. If you know what I mean, then you know what I mean. This is the usual pure Coulomb branch.
So you're saying something here, which is that if, okay, so G was a topological space before. So if G is an underlying topological space of, let's say, a complex semi-simple group, probably, is that what you want? And then in this case, this algebra you define purely using topology is the same as this one that's defined by BFN. Is that what you're saying?
Yes.
Okay.
Yeah.
It's a non-trivial statement. I don't think the connection was explained. It was asserted that this gives you the same algebra as the Coulomb branch for the group G with zero matter in the case when G is complex semi-simple group. I think that was the assertion, right?
Yes. So the alpha and Grassmannian kind of embed into this guy in a G equivariant G, which is G equivariant to the topic equivalent.
Or maybe even you're allowing G to be complex reductive. I don't know, is it? They have to be semi-simple.
Yeah, maybe.
Maybe reductive.
Yeah, I will give you an example.
Yes.
Yes. So and then so this is it turns out to be an algebra, a commutative algebra, and also finitely generated. And then you can take the spec, you get some variety, which turns out to be smooth. And then so it behaves like cohomology with respect to group, and there is a map from cohomology of BG to this guy. And if you take the spec, then you get a map backward. So you get this.
Oh.
I will give you an example. Let's see an example. So when you have a torus, the conjugation action is trivial. And then so then this guy splits. So you have the group part, you have the space part. The group is cohomology of BT. The space is homology of the basal space. And then cohomology for BT is just polynomial algebra. And then this is homology of basal space of T is just the group algebra of the fundamental group. And then you get this. So this is the space of algebraic function. This is because this homology theory. I'm not giving you a mathematic rigorous reasoning, but I'm saying that this behaves like cohomology with respect to group. So there is an upper star here, and it behaves like homology with respect to space.
One thing you can say is that we're trying to get algebras here. In fact, commutative algebras, but we're trying to get algebras. So in general, if you take a space, the homology isn't in general an algebra, but the cohomology is. So this BT, if you want to think of it as a space, its cohomology will be an algebra. This omega T has a special property coming from compositions of loops. That means that its homology is also an algebra. So this way, both of the tensor factors will be algebras. Is that correct?
Yes, yes. Then and then you can see the HI are the equivariant variable, and ZI are just oops. And then somehow I can write it in a funny way. I can write it as a functions on cotangent bundle of a complex torus. And if you keep track of the dual and if you keep track of this identification, you could put you will put a dual here, D dual, and then compressify. And then it actually has a natural algebraic sympletic form, but we will not use it. I just point it out. And the derivation that I mentioned earlier from this Coulomb branch to cohomology of BT is just the projection to the first factor. And the fiber are C star to the N. So the fibers are naturally groups.
True.
You consider this example?
What does it mean? It's quite
Yes.
Yeah, the trivial example. Yeah, it's quite trivial. Yes, trivial.
Then my next question is if you could discuss something which is not
Okay. Is it more non-trivial? ET is the classifying space, which is what is the, you can think of this as CP infinity in this case. So when you do
I think that you probably have heard some version of classifying spaces. So there's this idea that if you have say a vector bundle, or more generally a G bundle, then all of these are given have some classifying map to some space such that there's a universal bundle on it, and your bundle is given by pulling it back. You heard of something like that? In the case of line bundles, or alternatively T bundles, for T just C star, then this classifying space is just CP infinity. So there's the tautological bundle on CP infinity. The total space is C infinity, and every line bundle can be given by some map to CP infinity, pulling back that tautological bundle. And the class on cohomology, the class, the Chern class, is just the image of the generator of the cohomology of CP infinity under that pullback.
Yeah, to say product of CP infinity, sorry. So because
in this case, it's T to the n, so it's more than one CP infinity. If n was 1, it would be just CP infinity, this BT. But this BT is also what Bianchi was calling the Borel construction before. So given any group, there's this thing called Borel construction. Well, actually, you have a group and a space. In this case, just a group of this construction, which gives you a space whose cohomology is the equivariant cohomology of the group. So BT is the topological space whose ordinary cohomology is the equivariant cohomology, T equivariant cohomology of a point. That doesn't make sense, and I'm not sure.
Yeah.
The best way to say it. But in this particular case, you can think of BT as CP infinity to the nth power. Yes. Infinite projective space to the nth power. But in general, you're going to have some space whose cohomology will give you the equivariant cohomology of a point. Not sure if that helps. But maybe for now we should just, if you're not familiar with the BT, maybe we should try maybe we can just try to understand what its cohomology is, which in this case is much simpler than the space itself. So cohomology of BT is just a polynomial algebra and n variables here. Right. I think you can move on.
Okay. And then a non-abelian case. So
this is non-trivial now. When we go to non-abelian, I guess. The problem is that when you take Coulomb branch with 0 matter, right? If you're abelian, then you get a trivial situation.
So in this case, you take a maximal torus. This is not yet an example. I just tell you a recipe first, and then I will tell you an example. So you take a maximal torus, and then you look at roots and co-roots. So roots are some kind of linear function related to the adjoint representation. And then you have something also called co-roots. And then you can just think of there are some God-given linear functions. And then what you can do is if you take the exponential of so because a co-root I regard it as a function from the due of the Lie algebra complexification of the Lie algebra to C. If you put it on top and take exponential, then it will becomes a function on T check C on the complex torus.
Yeah.
And then alpha itself is a function from TC to C.
Yes.
And then so this guy makes sense as a rational function. And then the claim is that if you look at the T equivariant, not G equivariant, if you look at the T equivariant theory of omega G, G is non-abelian, but you look at the T equivariant theory, it is the same as this algebra, and then adjoining these extra variables, extra functions. Just make it bigger, give it more functions. And and then if you want to get the G equivariant version, there is a natural while group acting on this algebra. And then you take the invariant. So this is a recipe. I'm not explaining why. Actually, I don't know why. I didn't look at the proof. So that's the recipe. And then, okay. And so let's see an example. It's U2. You have a torus, S1 inside, and then you have this T star compressed torus. And then now we need to adjoin some function. So we have two pairs. So e to the alpha check becomes z, and then alpha becomes h in terms of these parameters, in terms of these variables. And then the other pair give you 1 over z and minus h. You put them into it. So you have an algebra with h, z, u, and v, and z inverse.
Mm-hmm.
And then you play with this, and then you realize that the only relation is this hv. You can get rid of z, and then you have huv, and then with the only relation being this. And then you do some computation, and then the while group.
Sorry, I want to make sure I understand. U and V
Yes.
are these expressions you had in the previous slide
Yes.
for the two different root covert pairs. But the two root and covert pairs are just the positive and the negative
Yes.
root, right?
Yes.
And so if you plug in the two different formulas, you get these two different answers for the additional elements you need to adjoin.
Yes, that's right. That's right. I just adjoin two more elements, u and v, into this algebra.
Okay.
So I will get a new algebra with c with h, z plus or minus 1, and then u and v, and they have some relation between them. And this is one relation. And you can see that from u and h, you can get rid of z because z equals u h plus 1. So z is not important now. And z inverse is also not important because h times v minus 1 equals to minus z inverse. So you can get rid of z and z inverse. So now your algebra is generated by h, u, and v. And then, but they have some relation. And then you can try, and you will see that the only relation is this relation.
Mm-hmm. But really, it's like just taking h and u, and then the v that you're adjoining is just like this fraction, u over 1 plus hu.
U over 1 plus hu. U over 1.
That v is equal to u over 1 plus hu. So you really just have hu and u over 1 plus hu. Right. I guess that's another way to think about it.
And then we can look at the while group action on this guy. So
If you put v to the other side, you get u is equal to v times 1 plus hu times v. So now we can, well, it's not maybe invertible, but just formally, it's the same as the ring generated by hu and the I see it. Mm-hmm. Yeah, so it is actually invertible. So actually, it is important that we're inverting that. So actually, we're taking the ring generated by hu, inverse of 1 plus hu, and that's it. And then the v is equal to the product of u and 1 plus hu inverse. That's a ring generated by hu and 1 plus hu inverse. It's actually generated by hu and z inverse. We do need the z inverse, it seems.
And then,
it's because you threw out the v. That's why we need the z inverse. If you threw out the u, you would need the z.
And then you can look at the action. It's actually swap U and V, and swap H to minus H. And then so the invariant thing is of course H squared is invariant. And then U plus V is invariant. U times V is also invariant. And then this K is actually the equivariant parameter of the BSU2 cohomology of the classifying space SU2. So you get this, you play with this, then you get this.
Do you know the relation of this going to
TAH spectral curve. I don't know a TAH spectral curve.
So when applying the zeros in the one.
You mean is it the same as AN?
D0, this is D0.
Oh, D0. Dn and n equal to 0? I don't understand.
I think it's the same thing with the singularity. It's the single surface, right?
So no.
Or maybe it's the resolution of this.
What is the thing you want? Which singularity?
For Dn, you have the n information.
Yes. You think this is resolution of Dn?
If we stop the discussion,
Okay. That's so then get this funny thing, and then and if you forget x and y, if you have k, x, y, and if you map it down to k, then it corresponds to the map from the spec of this to the spec of cohomology of BSU2. So you have some kind of affine variety, and then you have coordinate k, x, y, and then you just map to C by k. And then if you fix k, then generic fiber is C star. But there is some special fiber, which is C, and there is a canonical section, which is actually the to fiberwise, all of them are group. C star is a group, C is a group, and then you have an identity element in the group. So they form a section. And that's the case of SU.
And this is smooth. What we were discussing before, this is smooth, this space. Right?
Yes.
Even though we're taking a quotient by a group action was on something that was smooth, the result is also smooth in this case. I guess it was acting freely. Okay.
and for SU3, won't be that easy to write down.
Yeah, it's really more. I mean, I'm not good at algebra, so maybe it's easier for Travis. Yeah, it is. More.
But at least maybe can you estimate how many
Relations. Certainly one can try, but I haven't tried.
It's a very explicit description. I mean, I've seen lots of less explicit descriptions of this algebra. I think if you have matter, then it's even harder to get an explicit description than this. This doesn't seem that bad, actually. But yeah, you're right. Even this way, SU3 won't be super easy.
So how much time do I have?
Oh yeah, don't worry too much because we have until 1 and we'll take a break for lunch at some point.
Okay.
But,
And so yeah, people have already said that this is without matter. And then, so what if you put matter in? And then I think Parham, Finkelman, and Nakajima gave the first definition when mathematical definition when you have a cotangent type representation. And then, in their paper, they also describe how to understand the algebra, which Parliament kind of gave a reinterpretation. So roughly speaking, Parliament's reinterpretation is saying that you can sort of like bring 2 copies of the pure guy to get the non-pure one. But this is not true. We need to make it true. We need to make it a little bit more complicated. And let me describe how it goes. So first of all, so this guy, the T check and T together, this is just our cotangent bundle of compressed torus that we have seen a lot of time. So this is one pure Coulomb branch. And then for that guy, I cross with an extra direction. I consider C, cross with C. And this TC is the base of the derivation that I talk about. So the cohomology of the classifying space. And then I also cross it with an extra factor of C. So I kind of enlarge the vibration. And then I want to consider a section of this derivation. This section will be used to tell us how to group 2 copies of this guy together. We have 2 copies of this, and we want to group them together according to some rule that is determined by this section. And let's try an example where T is the most trivial possible. It's S1, and V is just Cn. And then you decompose it. You have weight and mu1 up to mu n. And I consider a very specific section of this derivation. So the derivation is going from the right to the left. I'm considering a section from the base to the total space. This section is given explicitly in this form. You have mu here, h here, and then some weight here, some kind of product. And then if you fix mu, then actually they are Lagrangian section. Anyway, I'm not using the algebraics. So there is a similar formula when you have an abelian high rank torus, a similar formula. And then what you do is you group 2 copies of them together using the section. The first factor is precisely the fibers of the vibration. So it has a group structure. In this case, it is just a compressed torus. It has a group structure. And then you group 2 copies of this guy using this transgrouring map. This is a map from this space to itself. It multiply the first factor by the section. By the way, this section is this section is only a meromorphic section. It is not necessarily well defined anyway. If you look at this formula, I have a new
Right.
in the power, so it might be negative. And then I just group in this way. And then I get a resulting space. And the functions on this space will give us an algebra denoted in this way. And this is a subalgebra of this. So this is the spec of this guy is precisely this. The spec of this one precisely this. And I am kind of enlarging my space, so I thought that I get a subalgebra of this algebra.
Oh, okay.
And then the Coulomb branch algebra is the fiber over 0 of this subalgebra, meaning the quotient by mu. So I kind of first thicken my derivation, do the GURing, get the algebra of function from the GURing, and then restrict it back to 0 section. With 0, 5. So some kind of some kind of recipe, but the key mysterious things is where this section coming from. Or maybe the entire thing is very mysterious. But I'm going to tell you.
How far did you see it's not symplectic anymore?
It is. You mean it's not algebraic symplectic?
No, the product of the three things is not. Yeah, the triple product is not symplectic. Yeah. Not algebraically symplectic.
So how important it needs to be regarded?
So
the section was a section. So this was a meromorphic Lagrangian section. Oh, it's already mu. So
yes.
Yeah, for fixed mu. So it's a family of Lagrangians indexed by C.
So you get then you kind of over these parameters mu, C mu, and then you kind of do this one parameter family of GURing. And then
then we have the ring of regular functions. Now we're thinking of this algebraically exclude thing.
Yes.
And taking its regular functions and modding by mu. Okay.
Yes.
Yeah, this is mysterious.
And the partners are not going
to be. No.
So we moved it along some identity element.
Along some identity element.
So when you group together two groups, fireworks.
Yes. I send the unit. I send the 1 to the section. I send the 1 to S. So
we're doing this STP as a gluing map. So if it were regular, then we would just glue the whole source to the target. But because it's meromorphic, we only glue the parts that are regular here to their image over there.
Yes, that's right. Yes.
Like making, I don't know, like making a sphere out of two hemispheres or whatever. Or overlapping hemispheres.
Yes. So, yeah.
Can you repeat the analysis in the relation?
Relation? With which relation? The algebraic relation. These relations. This is without matter, so these are the relation here. But then after you do such an operation, then it will be quite.
Yeah. So you, I'm sure that Amihai, you know very well how to compute the Coulomb branches SU2 for any representation, and Cheuk is claiming that whichever you get is going to be the ring of functions on this glued thing he's talking about. So I guess this could be verified probably.
Yeah, so this is the Telemann's reinterpretation of this BFN thing.
And if you take G to be this one, and then B to be this easier.
Well, I mean S1 instead of C star, I guess.
Yeah, I'm just using the calculator. I don't know.
So in the S1 case, you have this vibration, the vibration of C star except over 0 plus C. Right?
Yes.
And what kind of operation would you do in that case?
So it depends. You can. So essentially, you will get simple example is you have two copies of this C star cross C, and then the map go to C, and then only except 0, all the C star are identified. And then above 0, you have two disjoint C star. And then, but when you look at the algebra of functions on it and look at the spec, it will just close up the two C star, become a two line, two affine line. Does it make any sense? So,
So you're getting what, two lines glued together along the
So
C star? It's a non-separated version of the S1
so
What do you
you
say?
will get, I mean,
or S2.
so for one example is, so you have a lot of C star in your fiber. So only over 0, you have two disjoint C star.
Right.
But then, if you look at the functions on this space, so of course there is an extra parameter mu. Let's forget about this at the moment. And then, when you look at the space of function, and then look at the spec of that, it will give you one more point here, and then this guy will become this B.
Glued together at a point. I see.
Yes. And this is the user visualization picture for C2. So the total space becomes C2 if you forget about it.
Oh, I see. Okay.
Before you grew, it was C. C star. It was C.
This space is C, and then fiber are C star.
The fiber was over 0.
The fibers are C star, and the base is C.
Oh, I see.
Before, if I forget the mu, let's forget the
But
mu.
I think you're thinking of the SU2. Yeah, SL2. For SL2, we had a C over 0, but for during a abelian case, you had C star everywhere. And now we get two C stars at 0 because the map becomes meromorphic, right? So we don't glue them and everything else gets glued. And then you say, when you take affinization of this is not affine, take affinization, you're going to get this family of the coordinate axes deforming to the hyperbolas, right? And that gives you C2 as the total space.
Yes.
That's a complicated way of getting C2.
Yes. So,
Okay.
But presumably you can also get the resolution of the IC brackets.
I didn't try, but yes, one should be able to. So yes, I think so. Yes. So yes, that's right. It depends on the weight. if you change the weights, then yes, you are definitely right. Yes. Yes.
A resolution.
So, and then what am I talking about? So this is the abelian case, and the non-abelian case is similar. The non-abelian case, I just
So you're gonna get in other examples. So this this space, this algebraic space you're gonna get is a resolution of singularities, and so the ring of functions on it this will be symplectic resolution, I guess. So the ring of functions will be the ring of functions on the singularity, and that's what's gonna happen in general. You're saying?
yeah.
I see. Okay. So you actually construct the resolution, but your ultimate goal is to construct the singularity from the resolution instead of the other way around.
And then
So what were you saying on the previous slide? Did we get to all of that?
I think so.
Okay, right. Okay, so now we're back here. Okay.
And then back to non-abelian case. And the claim is that the recipe for non-abelian case is similar. So we take a maximal torus T inside, and then we have this abelian case here. And then this is this T equivariant of omega G is always the middle thing that we use all the time. So, and this is a algebra map. So you get a map network for the spec. And then you have some section in the, if you adjoin one more variable, meaning causing another C. So this guy, I've told you that there is some kind of section, meromorphic section. And then you take the Fourier transform of this. So this guy is obtained from this one by, so this one, remember, is obtained from this one by adjoining variable, adjoining some variable. So some kind of affine product. And then there's a way to get another thing inside here using the section here. And then the while invariant part will give you a meromorphic section with respect to this relation. And this is the non-abelian case. And you do the same thing. So you have some section, and fiberwise you have group structure, and then you can use the section to define the Turing map. And then that's the result of it's actually essentially in BFN paper, but Talon reinterpret this way. Okay. So
the proper transform of the image spec T omega G as a vial invariant meromorphic section. So proper transform means you took the image in H star T of omega T that we had before.
yes.
And now you're taking you're thinking of this as some kind of a birational map or something. You're taking the proper transform, taking some kind of closure of preimage over the locus where it's an isomorphism. That's right.
Yeah. So that's right.
Okay. And then you quotient by vowel group, and you get some map here, and you glue them together using that. And now you saying this is going to give you the general Coulomb branch.
Yes.
Doesn't matter.
Yes.
C0 smooth or
The CZO is a regular function, so looking at polynomial functions.
yeah.
Oh, the spec of it, not in general, right? Because this is going to be the yes, in general, this will be usually in most cases that that we've been studying them, the people in this room, it's been a cone. It's been functions on a cone which is generically symplectic. So in the case of the zero matter, it's not a cone, it's smooth and it was not a cone. But for most, if you have enough matter, usually you get the spectrum is usually a cone, which has some smooth symplectic locus, but then you have a cone point and you have some other finitely many symplectic leaves on this cone. Right?
Yes, please. So good that you are here to explain. So, and then, okay, finally, we arrived at the goal. So the goal is to tell you what is this section from the point of view of symplectic geometry. Using equivariant flow theory. It's essentially explained in Thailand, but we just make it rigorous. So, okay. So then this is the second part of my talk. I will talk about some symplectic geometry. So, but then where should we go for lunch?
Let's see. So, what time is it now?
It's almost 12.
Almost 12. Okay. Yeah. So, we have two options. We could go get lunch now and then do the second half of the talk, or we could continue. What do you?
Yes, how long do you plan for this?
Maybe half an hour.
Half an hour.
I don't know. It depends on how many questions you have.
Yeah, I guess that's it. So if it's an hour, also there's an issue of whether someone will come in the room at 1, but let's not worry about this issue right now. So if you think you can do it in only half an hour, I guess everybody's okay for finishing a talk and we all get lunch. But if you think you need more time, maybe we can get lunch first.
So from now it starts, I think it's gonna be loud.
Yeah.
How many slides are left?
Halfway through.
Yes, okay. So then maybe we should get lunch then. What do people think? That's a good idea. And then I will just check quickly whether someone's coming into this room at 1. And if so, we'll go somewhere. Well, I think I only asked the room to reserve until 1. But I will ask if there's someone coming here at 1 or not. If not, if no one's coming here, we can stay here longer. But otherwise, we'll just leave and continue discussing it elsewhere.
So that the lunch meetings, we go and get food and come back here.
Yeah, we'll go get lunch and bring it back here. Yeah, let's meet back in 15 minutes. Is it okay?
Yeah.
Yes, yes.
Yeah, we'll go get lunch, bring it here, and continue in 15 minutes.
Oh, yeah.